In this example, we are going to try to let R be the region bounded by the graph of y equals the square root of x. So here's our look. The x-axis and the vertical line of y equals 4. It says find the volume of the solid generated when R is revolved around the x-axis using disks and shells. So we're going to show both methods and kind of compare the two. Now, typically we use shells for something that is being rotated around the y-axis. And so we do that because everything starts off in terms of x's and we just want to leave everything in terms of x's. So this one is having us rotate around the x-axis, which means I probably wouldn't use shells because we're going to need to convert everything into terms of y rather than in terms of x. So let's go through shells and kind of show you here's why I probably wouldn't use it when I'm rotating stuff around the x-axis, but just to kind of give you a look that we could, but I don't think it's going to be the easier approach. So first thing is we need to turn things into terms of y's. And so if we take this equation, so I got two different situations or two different same graph, but this one I'm going to adjust. And so I have this y equals square root of x. So I'll square both sides. So y squared equals x. All right, so for shell, remember that your formula is, we're going to do the integral to pi x f of x dx, except we're going to make them y's. So for our volume, we're going to be doing 2 pi y. All right, and then what we have to figure out is that we're doing this approach. So we're going this direction. So our shells will be rotating around the x-axis, but we're going to take these shells to do that. And so here's where it gets even more complicated taking the shell route on this, is that we want these horizontal looks, but the problem is we have a gap that's missing. So we're going to have, for ours, our method is we're going to need to find the high function minus the low function. And so it's going to be a little more complicated than this. So we're going to need the high minus the low. And then d. So ours is going to be in terms of y's. So the high function is 4. Right? So that length right there would be 4. And we would be subtracting away this little bit each time. And that little bit each time is based on this equation, y squared. So that's the high, that's the low. So it would be 2 pi y times the high, which is 4, minus y squared, which is the low, or the long and the short. All right, so dy. All right, so already I'm not loving this method. Second part of this is everything has to be in terms of y. So we're going from this y value to up here. And that is if we plug 4 in and square root it, we get a y value of 2. So our bound is going to be 0 to 2. All right, so if we do the math here, we're going to pull the 2 pi out of this. We're still going to go from 0 to 2. We're going to go ahead and distribute that in. So that's a 4y minus y cubed dy. And if we do our antiderivative of that, we have a 2 pi, and we're going to add a power. So 4y squared divided by the 2 minus y to the 4th divided by the 4 from 0 to 2. So let's simplify that a little bit, and then we'll plug in our 2 and our 0. So 2 pi, this is going to be 2y squared minus just y to the 4th over 4. And then we'll plug in 0 and 2. So 2 pi. If I plug in 2 here, it's 2 squared, which is 4 times 2 is 8. Minus 2 to the 4th is 16 divided by 4 is 4. And then if I plug in 0, it's going to get a 0 out of that. And so this is going to be 4 times 2 pi. So we're looking at 8 pi for our volume. So not a great method because we had things in terms of x and we were rotating it around an x-axis. We could have left things in terms of x, which is what we're going to do for the disk. And instead, we had to shift it to the other variable because we were rotating around x and we were using shells. So we needed it in terms of y's. So kind of maybe not the best method. So let me show you the disk method that's going to get us the exact same answer. But here's what this thing looks like. So if we're doing disks, we're going to leave it in terms of x when we're rotating around the x-axis. And our volume is going to be more like a pi r squared times height. So this is a like true cylinders that we're creating with a thickness. So to find that from geometry, it's the area of the base times the height. And so that's going to be an integral of our R is going to be the equation, square root of x, and it's going to be squared. Our height is the thickness of these cylinders, which is dx, and we're going to go from 0 to 4. All right, so if I kind of rewrite this and clean this all up, I'm going to take the pi out always, 0 to 4, square root of x squared is x, and this is all that I'm doing the antiderivative of. I'm plugging in 4. So we would have add a power divided by power, x squared divided by 2 from 0 to 4. And so then we would get 4 squared of 16 over 2 minus 0 over 2, which 16 over 2, that's going to go away. 16 over 2 is 8. So our answer is 8 pi. So shell works great. But if I'm rotating around the x-axis, I'm probably always just going to leave it. If I'm rotating around the y-axis, there's definitely times and situations where I'm like, I think I'm just going to leave because these things are not easy to try and turn into y's. So let's just leave it alone and just take a little bit of a different approach, which really is just a little bit of a different formula, right? And so either I'm looking at that kind of a formula or I don't have just areas between curves. So then I'm just looking at this kind of a formula.